Welcome to all. I am G.SWETHA, Assistant Professor, Department of Physics, A.D.M.COLLEGE for Women, Autonomous NAGAPATTINAM. Today we learn about the subject is thermal physics, the topic thermodynamics. Table of the content. What is thermodynamics and the different branches of thermodynamics and basics concept of thermodynamics and the thermodynamic terms and the thermodynamic properties and the thermodynamic solved problems, laws of thermodynamics, and thermodynamics example in daily life, thermodynamics summary and overview, and frequently asked questions. Next, what is thermodynamics? The thermodynamics in physics is a branch that deals with heat, work and temperature and their relations to energy, radiations and physical properties of matter. And to be specified, it's explain how thermal energy is converted to or from other forms to energy and how matter is affected by this process. The thermal energy is the energy that comes from heat. This heat is generated by the movement of tiny particles within an object, and the faster these particles moves, the more heat is generated. It is based on the initial and final stage undergoing the changes. And next, different branches of thermodynamics. The thermodynamics is classified into the following 4 branches. The first, classical dynamics and statistical thermodynamics and chemical thermodynamics and equilibrium thermodynamics. Classical thermodynamics. It is classical thermodynamics. The behavior of matter is analyzed with microscopic approaches. The units such as the temperature and pressures are taken into the considerations, which helps the individuals calculate other properties and predict the characteristics of matter undergoing the process. Statistical thermodynamics. It is statistical thermodynamics. Every model is under the spotlight, that is the properties of every model and how they interact are taken into considerations to characterize the behavior of group of molecules. Chemical thermodynamics. The chemical thermodynamics is the study of how work and heat related to each other is chemical reactions and changes of states. Equilibrium thermodynamics. The equilibrium thermodynamics is the study of transformations of energy and matter as they approaches the state of equilibrium. Next, basics concept of thermodynamics is a thermodynamics terms. The thermodynamics has its own unique vocabulary associated with it. The good understanding of basic concept from a sound understanding of various topics discussed in the thermodynamic preventing possible misunderstandings. The figure is isolated boundaries. The first one is system boundaries. The boundary is a closed surface surrounding the system through which energy and mass may enter or leave the systems. And then the surroundings. What is surroundings? Everything that is interact with the system. And then system. The system is region containing energy and or matter that is spreaded from its surrounding by arbitrarily imposed walls of boundaries. Next, system. A thermodynamic system is a specific portions of the matter with a defined boundaries on which our attention is focused. The system boundaries may be real or imaginary, fixed or deformable. There are the 3 types of system. First one is isolated and closed and open. Isolated is cannot exchange both energy and mass with the surroundings. The universal is considered an isolated system. Now next, closed system. Across the boundary of closed system, the transfer of energy take place, but the transfer of mass does not take place. The refrigerated compressions of gas in the piston cylinder assembly or example of closed system. The open system is the mass and the energy, the both may be transferred between the system and the surrounding. A steam turbine is an example of open system. Next, thermodynamic process. A system undergoes the thermodynamic process when there is some magnetic energetic change within the system and that is associated with the change in pressure, volume and internal energy. There are the 4 types of thermodynamic process that have their unique properties, and they are: first, the adiabatic process, isochromic process and isobaric process and isothermal process. Adiabatic process where no heat transfer into or out of the system occurs, and isochloric process where no change in the volume occurs and system does not work. Isobaric process which no change in the pressure occurs. Isothermal process which no change in the temperature occurs. Next, thermodynamical equilibrium. At a given state, all properties of systems have fixed values. Thus, if the value of even one property changes, the system state change to be different one in a system that is in equilibrium. The no changes in the value of properties occur when it is isolated from its surrounding. They are the four types of thermodynamic equilibrium. When the temperature is same throughout the entire system, we consider the system to one first thermal equilibrium. Next, mechanical equilibrium is when there is no change in the pressures at any point of system, we consider the system. Next, chemical equilibrium. When the chemical composition of the system does not vary with the time, we consider the system. Next, phase equilibrium. The phase equilibrium is two phase of system is when the mass of each phase reaches an equilibrium level. Finally, the thermodynamical system is said to be the thermodynamical equilibrium if it is an equilibrium chemical, mechanical equilibrium and thermal equilibrium and the relevant parameters cease to the vary with the time. Next, thermodynamic properties. The thermodynamical properties are defined as the characteristics features of system capable of specifying under system state. The thermodynamical properties may be extensive and intensive. Intensive properties are properties that do depend on the quantity of matter, pressures, temperatures or intensive properties. In this case of extensive properties, their value depend on the mass of system, volume, energy, enthalpy or extensive properties. Thermodynamical properties are defined characteristics features of system capable of specifying the system state. The thermodynamic properties may be the extensive or intensive. They are the important properties of thermodynamicals. First one is what is enthalpy and the second one is what is entropy. The enthalpy is measurement of energy in a thermodynamical system. The quantity of enthalpy equal the total heat content of system. The equivalent to the system internal energy pulse the product of volume and pressures. The equation is H equal to E plus PV. Mathematically, the enthalpy H equal the sum of the internal energy E and the product of the pressure is P and volume of the V of the system. What is entropy? The entropy thermodynamical quantity whose value depend on the physical state or conditions of the system. In other words, it is the thermodynamical functions used to measure the randomness or disorder. For example, the entropy of solid where the particles are not free to move is less than entropy of a gases where particles will be container. Next, the laws of thermodynamics. There are thermodynamical laws define the fundamental physical quantities like energy, temperature and entropy. The characteristics thermodynamical systems at a thermal equilibrium. This thermal equilibrium's laws represent how this quantity behave under the various circumstances. How many laws of thermodynamics are there? The four laws of the thermodynamics and are given below. First one is Roth law of thermodynamics and first law of thermodynamics and second law of thermodynamics and third law of thermodynamics. The next few sections we will discuss each of this law of thermodynamics in default. First, the zeroth law of thermodynamics. The zeroth law of thermodynamics states that if two bodies are individually in equilibrium with a separate third bodies, then first two bodies are also in thermal equilibrium with each other. This means that is if system A is in thermal equilibrium with the system C and system B is also equilibrium with the system C, then system A and B are also is thermal equilibrium. An example of demonstrations in figure is zeroth law. Consider two caps of A and B with boiling water. When a thermometer is placed in a cup A, it is get warmed up by the water until it's read 100 degrees Celsius. When it is read 100 degrees Celsius, we say that the thermometer is in equilibrium with the cup A. When we move the thermometer to cup B to read the temperatures, it is continuous to read 100 degrees Celsius. The thermometer is also the equilibrium with the cup B. By keeping its mind the zeroth law of thermodynamics, we can conclude that the cup A and cup B are equilibriums with each other. The zeroth law of thermodynamics enable us to use thermometers to compare the temperature of any two objects that we like. Next, according to this law, some heat given to the system is used to change in the internal energy, while the heat rest is used in doing work by the system. It can be represented as mathematically as del Q equal del U plus W, where del Q is an heat given or lost, del U is the change in the internal energy, W is the work done. We can also represent the above equation as del Q equal del Q minus W. So we can infer from the above equations that the quantity del Q minus W is independent of the path taken to change in the state. Now further we say that internal energy tends to increases when the heat is given to the system and vice versa. And next, sign conservations. The table below show the approximated sign conservations of three equilibrium quantities under the different conditions. The first one is del U, change in the internal energy, and the second Q is heat and work done on the gases. Next, the first law of thermodynamics solved example showing here. Next, frequently asked question is thermodynamical. The basics questions showing here. Next, second law of thermodynamics. What is the second law of thermodynamics? The second law of thermodynamics states that any spontaneous occurring process will always lead to an acceleration in the entropy S of the universe. The simple words law explain that the isolated system entropy will never decreases over time, not less in some cases where the system is the thermodynamical equilibrium or going through a reversible process. The total energy of systems and its surrounding remaining constant. The second law is known as law of increased entropy. The second law of thermodynamical equations, mathematically del S universe lesser than 0, where del S universe is the change in the entropy of the universe. Third law of thermodynamics. The third law of thermodynamics states that the entropy of system approaches the constant value as the temperature approaches absolute zero. The entropy denoted by S is the measure of disorder and randomness in a closed system. It is directly related to the number of microstates. It is a fixed microscopic state that can be occupied by the system, accessible by the system. That is, the greater number of microstates the closed systems can occupy, the greater is entropy. The microstate is in which the energy of system is minimum is called ground state of system. At the temperature of 0 Kelvin, the following phenomena can be observed in the closed system. And the first, the system does not containing any heat. All the atoms and molecules in the system are at their lowest energy point. Therefore, the systems at absolutely zero has only one accessible microstate. It is ground state. As per third law of thermodynamical, in entropy of such a system is exactly zero. The show in figure. Next, the mathematical explanations of the third law. As per statistical mechanics, the entropy of systems can be expressed via the following equations. The equation is x minus s not equal to kb in ohms, where s is the entropy of the system, s0 is the initial entropy, kb denoted as the Boltzmann constants. The ohms refer to the total number of microstates that are consistent with the system microscopic configurations. Now for perfect crystals that has exactly one unique ground state, ohm equal to 1. Therefore, equations can be rewritten as follow: s minus s not equal to Kb, yeah, in bracket 1 equal to 0, because the in 1 is 0. When the initial entropy of the system is selected as 0, the following values of S can be obtained: S minus 0 equal to 0, greater than S equal to 0. Thus, entropy of the perfect crystals at absolute 0 is 0. Next, the thermodynamical example in daily life. Whether we are sitting in the air conditioned rooms or traveling in any vehicles, the applications of thermodynamical is everywhere. We have listed as the few of these applications below. The first, different types of vehicles such as the planes, tracks and ships works on the basics of the second law of thermodynamics. And the three modes of the heat transfer work on the basics of thermodynamics. The heat transfer concept are widely used in the radiators and heaters and coolers. And finally, thermodynamical is involved in the study of different types of power plants, such as the nuclear power plant and thermal power plants. Next, the thermodynamical summary and overview is simple terms, and thermodynamics deals with the transfer of energy from one form to another. It is the phase transitions. The laws of thermodynamics, or the first thermodynamics energy can either be created nor be destroyed. It can only be transferred from one form to another. And the second law of thermodynamics is entropy of any isolated systems always increases. And third laws of thermodynamics, the entropy of systems approaches a constant value as the temperatures approaches the absolute 0. And zeroth law of thermodynamics, if two thermodynamical systems are in thermal equilibrium, which third system separately are in the thermal equilibrium with equal others. Entropy is the measures of number of possible arrangement the atoms in the systems can have, and the enthalpy is the measurement of energy in the thermodynamical systems. Next, the importance frequently asked this question show in the slides. Thanking to all.